Scientists have been studying galaxies for many years. But why is after each discovery, we misunderstood what we had previously thought about this universe? It stretches out before us in ways that continue to challenge everything we thought we knew about the cosmos. For centuries, humanity has gazed upward at the night sky, attempting to comprehend the vast collection of stars, gas, and dust that populate the darkness beyond our atmosphere. What we call galaxies today were once mysterious cloudy patches that astronomers couldn't quite explain. And our journey to understanding them has been filled with misconceptions, incorrect assumptions, and dramatic revelations that completely overturned established scientific consensus. The story of how we misunderstood galaxies begins not with telescopes or modern technology, but with the naked eye observations of ancient civilizations who could only see a hazy band of light stretching across the night sky. This band, which we now know as our view of the Milky Way galaxy from within, was interpreted in countless ways by different cultures throughout history. The ancient Greeks believed this milky pathway was actually spilled breast milk from the goddess Hera, which gives us the name we still use today. Other civilizations saw it as a river, a road, or a bridge between earthly and divine realms. None of these early observers could have imagined that this faint glow was actually the combined light of hundreds of billions of stars, or that they were living inside a massive spiral structure rotating through space. The fundamental misunderstanding that plagued humanity for thousands of years was the belief that everything visible in the night sky was part of one single cosmic system centered around Earth or the Sun. Even as astronomy advanced and telescopes revealed increasingly distant objects, scientists struggled to grasp the true scale of the universe. When early telescopes began revealing fuzzy, cloud-like objects scattered throughout the heavens, astronomers grouped them into a category they called nebulae, from the Latin word for cloud or mist. They assumed these nebulae were relatively nearby clouds of gas within our own cosmic neighborhood, similar to the star-forming regions we can observe in places like the Orion Nebula. This assumption seemed perfectly reasonable, given the technology and knowledge available at the time. But it was fundamentally incorrect in ways that would take centuries to fully appreciate. One of the most significant misunderstandings arose from the work of 18th century astronomers who began cataloging these mysterious nebulous objects. Charles Messier, a French astronomer obsessed with discovering comets, created a famous catalog of fuzzy objects that kept interfering with his comet searches. His catalog, which included entries like Messier 31, Messier 33, and Messier 51, contained what we now know to be some of the most spectacular galaxies visible from Earth. But Messier and his contemporaries had no concept that these objects were anything other than clouds of gas and dust within the Milky Way. The technology simply didn't exist to resolve these fuzzy patches into individual stars, which might have provided a crucial clue about their true nature. The philosopher Immanuel Kant proposed in 1755 that some of these nebulous objects might actually be distant collections of stars similar to the Milky Way, which he called island universes. This was a remarkably prescient idea that correctly identified the nature of galaxies over a century before it could be proven. However, Kant's philosophical speculation was largely dismissed by the astronomical community because there was no observational evidence to support such an extraordinary claim. The instruments of the time couldn't resolve individual stars in these distant objects, and without that crucial piece of evidence, the island universe theory remained an interesting but unproven hypothesis. Most astronomers continued to believe that the entire universe consisted of the Milky Way and that all visible objects were part of this single system. This fundamental misunderstanding about the nature and extent of the universe persisted well into the 20th century, leading to one of the most famous debates in the history of astronomy. In 1920, two prominent astronomers, Harlow Shapley and Heber Curtis, engaged in what became known as the Great Debate at the Smithsonian Museum of Natural History in Washington. Shapley argued that the spiral nebulae were relatively small objects within our galaxy, while Curtis contended that they were separate galaxies far beyond the boundaries of the Milky Way. Both astronomers presented compelling evidence for their positions, and the astronomical community remained divided on this fundamental question about the structure of the universe. Shapley's position was based partly on observations of what he believed were nova explosions in the Andromeda Nebula. If these were ordinary novae, then Andromeda had to be relatively close, because the brightness of these explosions suggested they couldn't be at enormous distances. What Shapley didn't realize was that he was actually observing supernovae, which are far more luminous than ordinary novae and can be seen at much greater distances. This misidentification of the type of stellar explosion led him to dramatically underestimate the distance to Andromeda and to incorrectly conclude that it must be part of the Milky Way. This error demonstrates how a single misunderstood observation can lead astronomers down an incorrect path, affecting their entire understanding of cosmic architecture. The resolution to this debate came through the work of Edwin Hubble, who used the newly constructed 100-inch telescope at Mount Wilson Observatory in California to observe the Andromeda Nebula in unprecedented detail. In 1923 and 1924, Hubble identified individual variable stars in Andromeda, specifically a type called Cepheid variables. These stars have a remarkable property where their brightness varies in a regular pattern, and the period of this variation is directly related to their intrinsic luminosity. By measuring how bright these stars appeared and comparing that to how bright they actually were, based on their pulsation period, Hubble could calculate their distance using the inverse square law of light. His calculations revealed that Andromeda was approximately 900,000 light-years away, far beyond any conceivable boundary of the Milky Way. This discovery completely revolutionized our understanding of the universe. What astronomers had been calling the Andromeda Nebula was actually the Andromeda Galaxy, a massive collection of stars comparable in size to our own Milky Way. Suddenly, the universe had expanded tremendously in the minds of scientists and the public alike. We now know that Hubble's initial distance estimate was actually too small by more than a factor of 2. Modern measurements place Andromeda at approximately 2.5 million light-years from Earth. This error in Hubble's original calculation arose from complications in understanding Cepheid variables and from dust in our own galaxy that dims and reddens the light from distant objects. Even when we think we've corrected a major misunderstanding, we often discover that our new understanding still contains errors that need further refinement. The recognition that galaxies were separate island universes immediately raised new questions about the nature and variety of these cosmic structures. Hubble himself pioneered the systematic study of galaxy types, developing a classification scheme that astronomers still use today, with some modifications. He divided galaxies into elliptical galaxies, which appear as smooth, featureless ovals of light, and spiral galaxies, which show distinct arms of stars, gas, and dust winding outward from a central bulge. He also identified irregular galaxies that don't fit neatly into either category. This classification system seemed logical and straightforward, organizing galaxies based on their visual appearance. But it contained within it several fundamental misunderstandings about how galaxies form and evolve. Hubble initially thought his classification scheme might represent an evolutionary sequence, with elliptical galaxies perhaps evolving into spiral galaxies over time, or vice versa. This turned out to be incorrect. We now understand that galaxy types are primarily determined by their formation history and environment, rather than representing stages in a linear evolutionary sequence. Elliptical galaxies typically form through violent mergers of smaller galaxies, a process that scrambles the organized rotation of spiral galaxies and creates a more chaotic spheroidal structure. Spiral galaxies, meanwhile, maintain their distinctive shape through a delicate balance of rotation, gravity, and ongoing star formation. The transformation between these types is possible, but usually involves dramatic events like galaxy collisions, rather than gentle evolution from one form to another. Another major misunderstanding about galaxies emerged as astronomers began measuring their rotation speeds. In the 1930s, Fritz Zwicky studied the motion of galaxies in the Coma cluster and discovered something perplexing. The galaxies were moving so fast that the cluster should fly apart, unless it contained far more mass than could be accounted for by visible stars and gas. Zwicky proposed the existence of what he called dark matter to explain this discrepancy, but his idea was largely ignored for decades. The astronomical community wasn't ready to accept that the universe might be dominated by an invisible form of matter that couldn't be detected through any known means. The dark matter problem became impossible to ignore in the 1970s, when Vera Rubin and Kent Ford conducted detailed studies of galaxy rotation curves. They measured how fast stars orbit around the centers of spiral galaxies at various distances from the galactic core. According to the laws of gravity and the distribution of visible matter, stars farther from the center should orbit more slowly, just as outer planets in our solar system orbit more slowly than inner planets. But Rubin and Ford discovered that stars in the outer regions of galaxies were moving just as fast as stars closer to the center, sometimes even faster. This flat rotation curve violated everything astronomers expected based on the visible distribution of matter. This observation meant one of two things. Either our understanding of gravity was wrong on galactic scales, or galaxies contained enormous amounts of invisible matter extending far beyond the visible disk of stars and gas. Most astronomers concluded that galaxies must be embedded in massive halos of dark matter, invisible material that interacts with normal matter only through gravity. This realization meant that everything we could see in galaxies, all the stars and nebulae and dust clouds that make up the beautiful images in astronomy books, represents only about 15% of the total mass. The other 85% is dark matter, a mysterious substance that we still don't fully understand today. More than 4 decades after the rotation curve observations convinced the astronomical community of its existence. The misunderstanding about galaxy composition extends beyond dark matter to the space between galaxies. For many years, astronomers assumed that intergalactic space was essentially empty, a void containing perhaps a few stray stars ejected from their home galaxies, but otherwise devoid of matter. This assumption proved spectacularly wrong. Modern observations reveal that the space between galaxies contains vast quantities of gas, primarily hydrogen, that exists at extremely high temperatures. This gas forms an enormous cosmic web, with galaxies strung along filaments like beads on a string, separated by truly empty voids where almost nothing exists. The intergalactic medium contains more normal matter than all the stars in all the galaxies combined, though it's so diffuse and hot that it's essentially invisible to optical telescopes and can only be detected through specialized observations in X-ray and ultraviolet wavelengths. Our understanding of how galaxies form has undergone multiple revolutions as observations improved and theoretical models became more sophisticated. Early theories suggested that galaxies formed from the collapse of enormous gas clouds in the early universe, condensing into the structures we see today in a relatively straightforward process. This bottom-up formation scenario seemed logical, but turned out to be far too simple. Modern observations show that galaxy formation is a complex, hierarchical process where smaller structures merge to form larger ones over billions of years. The oldest galaxies we can observe in the distant universe look quite different from modern galaxies, appearing smaller, more irregular, and undergoing much more vigorous star formation. Today's giant elliptical and spiral galaxies are the result of countless mergers and interactions over cosmic time. The discovery that galaxies evolve and change dramatically over cosmic history revealed another layer of misunderstanding. When Hubble first observed distant galaxies in the early 20th century, there was an implicit assumption that galaxies were relatively stable structures that looked roughly the same throughout cosmic history. As telescopes improved and astronomers could observe increasingly distant and therefore increasingly ancient galaxies, it became clear that this assumption was completely wrong. Galaxies billions of years ago looked very different from galaxies today. They were smaller, more chaotic, forming stars at rates tens or hundreds of times faster than typical galaxies in the modern universe. The serene spiral and elliptical galaxies we see nearby represent mature structures that have undergone billions of years of evolution. Black holes represent another area where our understanding of galaxies was fundamentally incomplete for many years. The concept of black holes, regions of space where gravity is so strong that not even light can escape, emerged from Einstein's general theory of relativity in the early 20th century. However, for decades, black holes were considered theoretical curiosities rather than actual objects that might exist in nature. The idea that supermassive black holes, containing millions or billions of times the mass of the Sun, might lurk at the centers of most galaxies was not seriously considered until the latter part of the 20th century. Evidence gradually accumulated that something massive and compact occupied the centers of many galaxies. Astronomers observed stars orbiting around seemingly empty points in galactic centers at tremendous speeds, implying the presence of enormous concentrated masses. They detected powerful jets of energy shooting out from galactic cores and observed rapidly variable emissions that could only come from very compact regions. By the 1990s, the existence of supermassive black holes at galaxy centers had become widely accepted. But this raised new puzzles about how these monsters formed and how they influenced the galaxies around them. The relationship between supermassive black holes and their host galaxies turned out to be far more intimate than anyone expected. Observations revealed a tight correlation between the mass of a galaxy's central black hole and properties of the galaxy itself, particularly the velocity dispersion of stars in the galactic bulge. This correlation suggested that black holes and galaxies somehow grew together, each influencing the other's development. The mechanism behind this coevolution remained mysterious until astronomers developed detailed models of how black holes feed and how their feeding affects surrounding gas and stars. When material falls toward a supermassive black hole, it doesn't fall straight in, but instead forms a swirling accretion disk heated to millions of degrees by friction and gravitational compression. This process releases enormous amounts of energy, sometimes outshining the entire galaxy in which the black hole resides. The energy and powerful winds driven by the black hole can push gas out of the galaxy entirely, shutting down star formation and effectively regulating the growth of both the black hole and the galaxy. This feedback process means that supermassive black holes, despite containing only about 0.1% of a galaxy's mass, play a crucial role in determining what kind of galaxy forms and how it evolves over time. The discovery of active galactic nuclei, galaxies with extremely luminous cores, powered by supermassive black holes actively feeding on surrounding matter, revealed yet another aspect of galaxies that early astronomers had completely missed. Some of these active nuclei, called quasars, are so luminous they can be seen across the entire observable universe. When quasars were first discovered in the 1960s, astronomers were baffled by these point-like sources of light that seemed to be moving away from us at tremendous speeds based on the redshift of their light. The debate about what quasars actually were lasted for years, with some astronomers suggesting they might be nearby objects ejected from our galaxy at high speed. The eventual consensus that quasars were the brilliant cores of distant galaxies powered by supermassive black holes represented another major shift in understanding cosmic structures. Our misunderstanding of galaxies extended to the distribution of star formation within them. Early observations suggested that stars formed relatively uniformly throughout a galaxy's disk, but this turned out to be a significant oversimplification. Star formation in spiral galaxies is concentrated in the spiral arms, those graceful curved structures that give these galaxies their distinctive appearance. But the spiral arms themselves presented a puzzle that astronomers struggled to solve for decades. If the arms were simply material structures rotating with the galaxy, they should wind up tighter and tighter over time, as the inner parts of the galaxy rotate faster than the outer parts. After several rotations, spiral arms should become so tightly wound that they disappear. Yet we observe spiral galaxies with well-defined arms throughout the universe. The solution to this spiral arm puzzle came from density wave theory, developed by C.C. Lin and Frank Hsu in the 1960s. According to this theory, spiral arms are not material structures, but rather density waves, regions where stars and gas temporarily bunch together as they orbit the galactic center. Think of a traffic jam on a highway, where cars slow down and bunch together in a particular location, but the specific cars in the jam change as some leave and others enter. Similarly, material moves through the spiral arm density waves, spending more time in the denser regions and creating the appearance of persistent spiral structure. This elegant solution showed that spiral arms are dynamic, wave-like phenomena rather than fixed structures. Another example of how appearances can be deceiving in astronomy. The role of galactic environment in shaping galaxy properties took decades to fully appreciate. Early studies of galaxies naturally focused on nearby, isolated systems that were easier to observe in detail. This created a selection bias that led astronomers to develop theories based primarily on galaxies that weren't interacting strongly with neighbors. As surveys catalogued larger numbers of galaxies and their environments, it became clear that a galaxy's surroundings dramatically affect its properties and evolution. Galaxies in dense clusters differ systematically from galaxies in less crowded environments, tending to be more elliptical, more massive, and containing older stellar populations with less ongoing star formation. The processes responsible for these environmental effects include ram pressure stripping, where hot gas in galaxy clusters removes the cool gas from cluster galaxies as they plow through the intracluster medium, effectively starving them of the raw material needed to form new stars. Tidal interactions with neighboring galaxies can also strip away gas and disrupt galactic structure. Galaxy harassment, where multiple high-speed encounters with other cluster members gradually transform spiral galaxies into ellipticals, represents another important environmental process. These discoveries showed that galaxies cannot be understood in isolation, but must be studied as parts of larger cosmic structures. The phenomenon of galactic cannibalism, where large galaxies grow by consuming smaller neighbors, represents one of the most dramatic examples of galaxy evolution that early astronomers completely missed. When Hubble developed his classification system, there was an implicit assumption that galaxies were stable objects that maintained their basic form over time. We now know that galaxy mergers are common throughout cosmic history, and play a crucial role in building the most massive galaxies we observe today. The process of galaxy merging can be surprisingly complex, with smaller galaxies sometimes surviving as distinct structures within their larger hosts for billions of years before finally being completely absorbed. Evidence for ongoing galactic cannibalism surrounds us in our local cosmic neighborhood. The Milky Way itself is currently in the process of consuming several smaller satellite galaxies, including the Sagittarius Dwarf Elliptical Galaxy, which is being torn apart by our galaxy's gravity. Long streams of stars from this disrupted galaxy wrap around the Milky Way like ribbons, marking the path of its gradual destruction. The Magellanic Clouds, two small irregular galaxies visible from the southern hemisphere, are also being gravitationally perturbed by the Milky Way and may eventually merge with our galaxy billions of years from now. These interactions show that even our own galaxy is not an isolated, static structure, but rather a dynamic system that grows through the incorporation of smaller companions. The understanding that the Milky Way itself is just one galaxy among billions, each containing billions of stars, profoundly changed humanity's perspective on our place in the universe. This realization came gradually over the first half of the 20th century as the scale of the universe became apparent. The philosophical and cultural impact of understanding that our galaxy is not unique or special, that the universe contains hundreds of billions of galaxies stretching as far as we can see in every direction, represents one of the most significant shifts in human thought in history. We are not just residents of one planet among many in our solar system, or even one solar system among many in our galaxy, but one solar system in one galaxy among countless others scattered throughout an almost incomprehensibly vast universe. The discovery that the universe is expanding added another layer of complexity to our understanding of galaxies. Edwin Hubble's observation in 1929 that distant galaxies are moving away from us, with more distant galaxies moving away faster, revealed that space itself is expanding, carrying galaxies along with it. This discovery implied that the universe had a beginning, some finite time in the past, when everything was much closer together. The Big Bang theory, which describes the universe emerging from an extremely hot, dense state approximately 13.8 billion years ago, emerged from this observation of cosmic expansion. Galaxies form from slight density variations in the early universe that grew over time under the influence of gravity, eventually collapsing into the structures we see today. The existence of gravitational lensing, where the gravity of massive galaxies and galaxy clusters bends light from more distant objects, revealed both the distribution of dark matter and the existence of galaxies too distant and faint to detect directly. When a massive foreground galaxy lies nearly along our line of sight to a more distant background galaxy, the foreground galaxy's gravity can bend and magnify the light from the background galaxy, sometimes creating multiple images or even a complete Einstein ring where the background galaxy's light forms a circle around the foreground lens. These natural cosmic telescopes allow astronomers to study galaxies that would otherwise be completely undetectable, revealing the universe at earlier times in its history. The detailed mapping of gravitational lensing effects also provides one of the best ways to measure the distribution of dark matter in galaxy clusters, as the lensing depends on total mass rather than just visible matter. Our understanding of the chemical evolution of galaxies represents another area where initial assumptions proved inadequate. The first stars to form in the early universe were composed almost entirely of hydrogen and helium, the elements created in the Big Bang. All heavier elements, what astronomers collectively call metals, regardless of their actual chemical properties, were synthesized inside stars through nuclear fusion and scattered into space when massive stars exploded as supernovae. This means that subsequent generations of stars, incorporated these heavier elements, and the metallicity of stars in a galaxy provides a record of the galaxy's star formation history. Early theories suggested that galaxies should show a simple relationship between age and metallicity, with older stars being metal-poor and younger stars being metal-rich. However, observations reveal a much more complex picture, with significant variations in metallicity at all ages, reflecting the complex mixing of gas from different sources, including supernova ejecta, gas accreted from intergalactic space, and material stripped from satellite galaxies. The role of supernova feedback in regulating star formation within galaxies took decades to fully appreciate. When massive stars explode as supernova, they don't just enrich the surrounding gas with heavy elements, but also inject enormous amounts of energy that heats the gas and drives powerful winds. This energy input can blow gas out of small galaxies entirely, or at least disrupt gas clouds and prevent them from collapsing to form new stars. Without this feedback process, theoretical models predict that galaxies should convert their gas into stars far more efficiently than observations indicate actually happens. The inclusion of supernova feedback in galaxy formation models was a crucial step in developing theories that could match observed galaxy properties, particularly for low-mass galaxies, where supernova energy is most effective at driving gas out of the galaxy's gravitational potential well. The discovery that some galaxies undergo dramatic starbursts, episodes of extraordinarily rapid star formation, consuming a galaxy's gas reservoir in just a few 100 million years, revealed another aspect of galaxy evolution that wasn't captured in early smooth, gradual models. Starbursts typically occur when galaxy mergers funnel large amounts of gas toward the galactic center, where it collapses to form stars at rates up to 100 times higher than typical spiral galaxies like the Milky Way. These starburst galaxies appear bright at infrared wavelengths because dust absorbs the ultraviolet light from young massive stars and re-radiates it in the infrared. The recognition that starbursts represent an important mode of star formation, particularly at earlier times in cosmic history, required a fundamental rethinking of how galaxies build up their stellar populations over time. The existence of ultra-diffuse galaxies, enormous galaxies containing very few stars spread over vast volumes of space, represents one of the most recent surprises in galaxy studies. These ghostly galaxies can be as large as the Milky Way, but contain only about 1% as many stars, making them extremely difficult to detect despite their large size. Their discovery challenged assumptions about minimum surface brightness, limits for galaxies, and raised new questions about galaxy formation. How do these tenuous structures form, and why don't they collapse into denser, more typical galaxies? The answers likely involve both dark matter, which provides the gravitational scaffold holding these galaxies together, and powerful feedback processes that prevented much gas from turning into stars. But the details remain actively debated. The study of galaxy stellar halos, the diffuse outer regions of galaxies populated by old stars, revealed another component of galactic structure that wasn't appreciated in early observations. These halos extend far beyond the visible disk or bulge of galaxies and contain fossil records of past merger events, encoded in the motions and compositions of individual stars. By studying stellar halos in detail, astronomers can reconstruct the merger history of galaxies, identifying the remnants of cannibalized satellite galaxies, and learning about the assembly process that built modern large galaxies. The realization that stellar halos contain such valuable archaeological information transformed them from barely noticed features to subjects of intense study. Dwarf galaxies, the most common type of galaxy in the universe, were systematically underappreciated in early galaxy studies because they're so faint and inconspicuous compared to giant spirals and ellipticals. However, dwarf galaxies play crucial roles in galaxy evolution as the building blocks from which larger galaxies form through hierarchical assembly. They're also laboratories for studying dark matter, as the smallest dwarf galaxies are the most dark matter-dominated objects known, with mass-to-light ratios suggesting that dark matter outweighs visible matter by factors of hundreds or even thousands. The discovery of numerous dwarf galaxies orbiting the Milky Way and Andromeda revealed the rich satellite systems surrounding large galaxies and provided important tests for cosmological models. The tension between observed and predicted numbers of satellite galaxies around the Milky Way represents an ongoing puzzle known as the missing satellites problem. Simulations of galaxy formation in a universe dominated by cold, dark matter predict that large galaxies should be surrounded by thousands of small dark matter halos. But astronomers have only detected a few dozen satellite galaxies around the Milky Way. Either most of these predicted satellites are too faint to detect even with current surveys, or something about the galaxy formation process prevents the formation of stars in most small dark matter halos. Or perhaps our understanding of dark matter properties needs revision. This discrepancy illustrates how observations continue to reveal shortcomings in our theoretical understanding of galaxies. The realization that many early-type galaxies contain unexpected populations of young stars challenged the traditional view that elliptical galaxies are red and dead systems that exhausted their gas and ceased forming stars billions of years ago. Observations of blue elliptical galaxies and detection of ongoing star formation in some early-type galaxies forced a more nuanced view of galaxy evolution. Some ellipticals do appear to be completely quiescent, containing only old stellar populations, but others show evidence of recent gas accretion and renewed star formation. The diversity of early-type galaxy properties suggests that multiple formation channels lead to similar final morphologies. Another example of how oversimplified classification schemes can obscure underlying complexity. The discovery of Green Valley galaxies, systems with properties intermediate between actively star-forming blue galaxies and quiescent red galaxies, revealed a population in transition from one state to the other. Understanding what drives galaxies through this transition represents a major question in modern galaxy evolution studies. Possible mechanisms include exhaustion of gas supplies, removal of gas by environmental processes in galaxy clusters, or active galactic nucleus feedback that heats or expels star-forming gas. The relatively small number of Green Valley galaxies suggests that the transition happens relatively quickly on cosmic timescales, implying some rapid quenching process rather than gentle, gradual decline in star formation. The role of cosmic magnetic fields in galaxies represents another aspect that was not included in early models, but has proven important for understanding galaxy structure and evolution. Magnetic fields in galaxies are not particularly strong by laboratory standards, measuring just a few microgauss, but they pervade the entire galactic disk and play important roles in regulating star formation, supporting gas clouds against gravitational collapse, and accelerating cosmic rays. The origin and maintenance of these magnetic fields involves complex dynamo processes operating over billions of years, converting kinetic energy from turbulent gas motions into magnetic energy. Understanding galactic magnetic fields requires combining observations at radio wavelengths, where synchrotron emission from cosmic ray electrons spiraling in magnetic fields can be detected, with sophisticated theoretical models of magnetohydrodynamic processes. The recognition that galactic bars, elongated central structures found in many spiral galaxies, including the Milky Way, play important roles in galaxy evolution came relatively late in the study of galaxies. Bars can channel gas from the outer disk toward the galactic center, fueling both star formation and black hole growth. They can also scatter stars and alter the structure of the galactic disk, The formation and dissolution of bars occurs over billions of years and depends on the distribution of dark matter, the gas content of the disk, and interactions with satellites or companion galaxies. The discovery that the Milky Way itself possesses a prominent bar challenged older ideas about our galaxy's structure and required revisions to models of the galactic gravitational potential. The phenomenon of ram pressure stripping, where galaxies moving through the hot gas-pervading galaxy clusters lose their own cool gas, represents a dramatic example of environmental effects on galaxy evolution. When a spiral galaxy falls into a massive cluster, it can plow through the intracluster medium at speeds of thousands of kilometers per second. The pressure of this hot gas pushes against the cool gas in the galaxy's disk, like wind removing leaves from a tree. This process can strip away most of a galaxy's star-forming gas in just a few 100 million years, transforming a blue spiral galaxy into a red, quiescent system. The spectacular jellyfish galaxies, where long tentacles of stripped gas trail behind the galaxy, like the tentacles of a jellyfish, provide dramatic visual evidence of this process in action. The existence of fossil groups, galaxy systems that appear to be groups based on their X-ray emission from hot gas but contain only one or two luminous galaxies, suggests that hierarchical merging has already assembled most of the member galaxies into a single massive system. These structures represent the end stages of galaxy group evolution and provide laboratories for studying how repeated mergers shape the properties of the most massive galaxies. The realization that fossil groups represent a distinct class of structures rather than just unusual outliers required systematic surveys of galaxy groups and detailed studies of their properties. The study of ultra-compact dwarf galaxies and their relationship to globular clusters represents an active research area that has revealed unexpected complexity in the populations of objects orbiting large galaxies. These systems occupy a mass and size range intermediate between typical globular clusters and dwarf galaxies, and their origin remains debated. Some may be genuine dwarf galaxies that have been tidally stripped down to just their dense cores, while others might represent unusually massive globular clusters. The existence of objects spanning the gap between star clusters and galaxies illustrates how nature doesn't always fit neatly into the categories astronomers create. The impact of cosmic rays on galaxy evolution has become increasingly appreciated in recent years. These high-energy particles, accelerated in supernova remnants and other energetic environments, pervade the galactic disk and carry enough energy to significantly affect gas dynamics. Cosmic rays can provide additional pressure support for gas clouds, alter the conditions for star formation, and drive galactic winds that remove gas from galaxies. Including cosmic rays in theoretical models of galaxy evolution has proven challenging because their behavior involves complex physics, but models that include cosmic ray effects can better match observed properties of galaxies, particularly the inefficiency with which galaxies convert their gas into stars. The observation that the star formation rate in the universe peaked about 10 billion years ago and has been declining ever since revealed important constraints on galaxy evolution models. This cosmic star formation history reflects the interplay between gas accretion onto galaxies, consumption of gas through star formation, and removal of gas through feedback processes. The decline in cosmic star formation, despite ongoing gas accretion, suggests that feedback processes have become increasingly effective at preventing star formation as the universe evolved. Understanding the physical mechanisms responsible for this global evolution in star formation requires combining observations of galaxies at all cosmic epochs with sophisticated theoretical models. The role of environmental quenching in producing the populations of red, quiescent galaxies observed in massive galaxy clusters took decades to fully understand. Multiple physical processes contribute to shutting down star formation in cluster galaxies, including ram pressure stripping of gas, tidal interactions that disrupt galactic structure, galaxy harassment through repeated high-speed encounters, and starvation, where the hot intracluster medium prevents fresh gas from accreting onto cluster galaxies. Disentangling the relative importance of these various mechanisms requires detailed observations of galaxies at different stages of infall into clusters and sophisticated models of the relevant physical processes. The discovery that some massive elliptical galaxies at high redshift are extremely compact, with sizes several times smaller than equally massive ellipticals in the nearby universe, revealed that galaxies can grow substantially in size even after most of their stars have already formed. This size evolution likely occurs through minor mergers, where small satellite galaxies are accreted and their stars join the outer parts of the massive galaxy, increasing its overall size without adding much mass. The recognition that galaxies can evolve significantly in size challenged earlier assumptions that galaxy structure is fixed once the bulk of stars have formed. The study of tidal dwarf galaxies, objects that form from material stripped from larger galaxies during mergers and interactions, revealed another mode of galaxy formation, distinct from the hierarchical assembly of dark matter halos. These systems form in regions of high gas density within tidal tails pulled from interacting galaxies. Unlike typical dwarf galaxies, tidal dwarfs contain little or no dark matter because they form from baryonic material pulled from the outer disks of their parent galaxies, regions where dark matter density is relatively low. The existence and properties of tidal dwarfs provide important tests of galaxy formation theories and constraints on the nature of dark matter. The role of active galactic nuclei in driving large-scale outflows that affect galaxy evolution has become increasingly clear from recent observations. Some of the most powerful active galactic nuclei drive winds that carry enormous quantities of gas out of their host galaxies at speeds of thousands of kilometers per second. These outflows can extend for tens of thousands of light years and contain enough energy to unbind gas from even the most massive galaxies. The mechanical energy from these winds, supplemented by radiation pressure from the luminous accretion disk around the central black hole, provides a mechanism for active galactic nucleus feedback to regulate both black hole growth and star formation in the host galaxy. The discovery that some galaxies exhibit counter-rotating components, where different parts of the galaxy rotate in opposite directions, revealed complex formation histories involving accretion of gas with angular momentum misaligned with respect to the galaxy's initial rotation. These systems provide valuable information about gas accretion processes and the role of mergers in shaping galaxy structure. The existence of counter-rotating components was not anticipated by early simple models of galaxy formation, but emerges naturally from hierarchical assembly models, where galaxies grow through mergers and accretion of material from diverse sources. The phenomenon of galactic fountains, where supernova-driven winds eject gas from the galactic disk, only to have it fall back at later times, represents an important cycle that enriches the galaxy with heavy elements and regulates star formation. Gas blown out of the disk by supernovae cools as it rises into the galactic halo, eventually falling back due to gravity. This cycling of material between the disk and halo helps mix newly synthesized elements throughout the galaxy, and may trigger new episodes of star formation when enriched gas returns to the disk. Understanding galactic fountains requires three-dimensional hydrodynamic simulations that can track gas over millions of years as it cycles through different phases. The realization that cosmic reionization, the process by which ultraviolet light from early stars and galaxies ionize the neutral hydrogen pervading the universe in its first billion years, fundamentally affected subsequent galaxy formation, represented an important development in understanding early cosmic history. Before reionization, gas could cool efficiently and collapse into low-mass dark matter halos, forming the first small galaxies. After ionization, the ionized intergalactic medium became much hotter, preventing gas from collapsing into the smallest dark matter halos and effectively shutting down the formation of the smallest galaxies. This process helps explain why we don't observe even more dwarf galaxies than we already see, and illustrates how global cosmological processes affect local galaxy formation. The discovery of population 3 stars, the very first generation of stars that formed in the universe, composed entirely of hydrogen and helium without any heavier elements, remains one of the holy grails of observational astronomy. These primordial stars are predicted to have been much more massive than typical stars today, perhaps hundreds of times the mass of the Sun, and would have lived extremely short lives before exploding as supernovae. The search for these first stars involves looking at the most distant galaxies we can observe, hoping to catch glimpses of these massive luminous objects before they died. While individual population 3 stars have not yet been definitively detected, their existence is inferred from the chemical patterns observed in the oldest known stars in our galaxy, which show the signatures of enrichment by these early massive stars. The role of turbulence in the interstellar medium of galaxies represents another aspect of galactic physics that has gained increasing attention in recent decades. The gas in galaxies is not smooth and uniform, but rather exists in a highly turbulent state, with complex motions on all scales, from parsecs to kiloparsecs. This turbulence affects virtually every aspect of galaxy evolution, from the formation of molecular clouds, where stars are born, to the propagation of supernova shockwaves through the galactic disk. Understanding the sources of turbulence, which include supernova, stellar winds, gravitational instabilities, and accretion of external gas, and how turbulence dissipates over time, requires sophisticated numerical simulations that can capture the complex multi-phase structure of the interstellar medium. The importance of molecular gas, particularly molecular hydrogen, in star formation took many years to fully appreciate, because molecular hydrogen is extremely difficult to observe directly. This molecule has no permanent dipole moment, and therefore produces very weak emission lines that are undetectable in cold molecular clouds where star formation occurs. Instead, astronomers must use tracer molecules like carbon monoxide to map the distribution of molecular gas in galaxies. The realization that essentially all star formation occurs in molecular clouds rather than in the atomic hydrogen gas that pervades galactic disks required the development of radio telescopes sensitive to millimeter wavelengths where molecules emit. This discovery showed that the conversion of atomic to molecular hydrogen represents a key bottleneck in the star formation process. The existence of extended ultraviolet disks around some spiral galaxies, regions of star formation extending far beyond the optical disk where most stars are located, challenged the traditional view that star formation is confined to the bright inner regions of galaxies. These extended ultraviolet disks show that under certain conditions, gas in the outer regions of galaxies can become dense enough to collapse and form stars, even though the overall gas density is much lower than in the inner disk. Understanding what triggers star formation in these low-density environments has implications for how galaxies grow and for the distribution of stellar populations across galactic disks. The discovery of hypervelocity stars, individual stars moving through our galaxy at speeds high enough to escape the Milky Way's gravitational pull, provided direct evidence for the dramatic dynamical processes operating in galactic centers. These stars are thought to have been part of binary systems that wandered too close to the supermassive black hole at the galactic center. The black hole's gravity disrupted the binary, capturing one star while flinging the other outward at tremendous speed. The existence of hypervelocity stars confirms theoretical predictions about the chaotic dynamics near supermassive black holes, and provides a way to probe the mass and properties of the central black hole through the trajectories of ejected stars. The observation that some galaxies contain multiple stellar populations with distinct ages and chemical compositions revealed the episodic nature of star formation in many systems. Rather than forming stars continuously at a relatively steady rate, many galaxies experienced periods of intense star formation, separated by quiescent phases. These bursts and lulls in star formation activity can be triggered by various processes, including galaxy mergers, gas accretion events, or internal dynamical processes like bar formation. The ability to date stellar populations in nearby galaxies through detailed observations of their constituent stars allows astronomers to reconstruct the star formation histories of these systems and test theories of galaxy evolution. The role of intermediate mass black holes, objects with masses between stellar mass black holes formed from individual stars, and the supermassive black holes found in galaxy centers, remains one of the outstanding puzzles in understanding black hole populations. If these intermediate mass black holes exist, they might represent the seeds from which supermassive black holes grow, but direct evidence for their existence has been elusive. Possible detections include unusual X-ray sources in nearby galaxies and massive black holes in the centers of some globular clusters, but definitive confirmation of intermediate mass black holes remains challenging. Understanding how supermassive black holes grew to contain millions or billions of solar masses in the first billion years of cosmic history may require these intermediate mass seeds. The discovery that some galaxies are dominated by dark matter to an even greater extent than typical systems, with dark matter fractions approaching 99%, has raised new questions about galaxy formation in the faintest systems. These ultra-faint dwarf galaxies contain only a few thousand stars, making them barely visible even with the largest telescopes. Yet their dynamics indicate they must be embedded in dark matter halos containing millions of times more mass than their visible stellar content. The existence of such dark matter-dominated systems provides crucial tests of cosmological models and insights into the physics of star formation in the smallest galaxies. The investigation of polar ring galaxies, systems where a ring of stars, gas, and dust orbits perpendicular to the main galactic disk, revealed another exotic configuration that challenges simple models of galaxy formation. These systems likely form when a galaxy accretes material with angular momentum oriented perpendicular to its own rotation axis, perhaps through the tidal disruption of a passing companion galaxy. The existence of stable polar rings demonstrates that galaxies can maintain multiple distinct kinematic components for billions of years, and provides unique opportunities to study the three-dimensional distribution of dark matter in galaxies. The phenomenon of galactic winds driven by intense star formation activity represents another important feedback mechanism that wasn't fully appreciated in early galaxy models. When star formation proceeds at extremely high rates, as occurs in starburst galaxies, the combined effects of thousands of supernovae and stellar winds can drive a large-scale outflow that removes gas from the galaxy. These winds can reach velocities of hundreds or thousands of kilometers per second and can extend for tens of thousands of light years beyond the galactic disk. The mass loading factor, which describes how much gas is ejected relative to how much is turned into stars, plays a crucial role in regulating galaxy growth and determining the efficiency of star formation across cosmic time. The study of intracluster light, diffuse stellar populations that fill the space between galaxies in massive clusters, revealed yet another component of cosmic structure that early observations missed entirely. This light comes from stars that have been stripped from cluster galaxies through tidal interactions and now orbit freely in the cluster's gravitational potential. The fraction of light in the intra-cluster component can reach 20 to 40% in some clusters, representing a significant reservoir of stars that don't belong to any individual galaxy. The existence and properties of intra-cluster light provide important constraints on the dynamical history of galaxy clusters and the efficiency of tidal stripping processes. The realization that galaxies can experience morphological transformations through processes other than major mergers expanded our understanding of how galaxy types change over time. Minor mergers, where small satellite galaxies are gradually accreted, can also alter galaxy structure, though more slowly and less dramatically than major mergers. Disk instabilities can drive the formation of galactic bars or spiral arms without any external perturbation. Even isolated galaxies can evolve in morphology as their gas content changes and as internal processes redistribute mass within the system. The recognition that galaxy morphology is not fixed but continues to evolve throughout cosmic history represents a major shift from the static view implicit in early classification schemes. In examining how we misunderstood galaxies, we see a pattern repeating throughout the history of astronomy. Initial observations with limited technology lead to reasonable but incorrect assumptions about what we're seeing. As technology improves and observations become more detailed, these assumptions are challenged and eventually overturned, often revealing a universe far more complex and surprising than anyone imagined. Our current understanding of galaxies, while far more sophisticated than anything available to earlier generations of astronomers, undoubtedly contains errors and oversimplifications that future observations will reveal. The history of studying galaxies teaches humility about the limits of current knowledge, while celebrating the scientific process that gradually reveals the true nature of the cosmos, layer by layer, surprise by surprise, misconception by misconception, corrected through patient observation and theoretical insight.